Okay, so a quick summary of what we've done so far. We started out calculus by trying to work out the derivative of y equals x to the power of 2. We did it by setting up this system here, where we have points A and B, and then the average gradient that exists between A and B is given by this. But then to find out the true gradient, we had to take the limit as h tends to 0. Okay, so this bit here is called differentiation by first principles, and then we use the same method for y equals x to the power of 3. We set up this system, set up 2 points A and B, and then the average gradient that exists between A and B is given by this. But then the true gradient that exists at A is when we start to take the limit as h tends to 0, and then we use this to work out the differential of y equals x to the power of 3. And then we use the same technique for y equals 1 over x. And again, set up this system, set up A and B. The average gradient that exists between A and B is given by this, but then the true gradient is when you start to take the limit of as h tends to 0. And then we moved on to something complicated, like this here. Suppose you have y equals blah 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 here. We could do this. We could differentiate it by using first principles here. We could use this, but you see this bit here is very tedious. Having to work this out takes a lot of work here. So we use one of the theorems that allows us to just differentiate this, differentiate this all separately, and then get this, take away this, and then but basically rather than when given something complicated like this, rather than working it all out like this, we could just differentiate this, and differentiate this all separately. Okay, so one of the theorems allows us to do that, so it saves us having to do this all the time. Okay, and then we moved on to what we then moved on to y equals x to the power of n. And I've always asked you to take my word for the time being that when you try to differentiate this, I've always asked you to just take my word for it for the time being, to take this n down here and then minus the power by 1. So I've always asked you to accept it for the time being. When you differentiate this, it becomes this, always minus 1. And I never really explained why. But then up until now, I've explained why this works for the case of n being a number, an integer greater or equal to 1. So I've done a proof for this case here. Okay, we've done a proof on a case where you have x to the power of, let's say, 2, x to the power of 3, x to the power of 4. We know why this works when x is a whole number greater or equal to 1. But we haven't done a proof on when x when you have x to the power of a fraction like this. This I will do another time, coming soon. Okay, and we haven't done this either. We haven't. I've always asked you to just, okay, when you differentiate this, just this will then become n minus 7x to the power of minus 8. I've always asked you to just accept it for the time being, but I've not done a proof yet. So this here will be coming soon, okay, and something like this here will be coming soon as well. Okay, so all that I've proved so far is when n is an integer, where n is greater or equal to 1. Okay, but then our next aim is to work out this. So I've still got to show you these three. Okay, I've still got to prove these three to you, and but then our next aim is really to find out the derivative of sine of x. So to find out the derivative of y equals sine of x, we will set up our system like this, and then set up 2 points A and B, the average gradient that exists between A and B, blah blah blah, and then to find out the true gradient, we have to take the limit as h tends to 0. But the thing is, this bit here is actually quite difficult here. We need to be able to break this bit up here, this sine x plus another number here. We need to develop a way to break this bit up in order to work out the derivative of this. Okay, I'll explain this as time goes on, and then we also have to we also have to find the derivative of cos of x here. So we would set up this system, a and b here, the gradient that exists between a and b, blah 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 blah, and then to find out the true gradient we have to take the limit as h tends to 0. But then this bit here is quite difficult. We need to develop a way to break this apart. We need to develop a way of breaking a plus b. So we need to find a way to break this up. Okay, so that's our next aim. Our next aim is to find our aim is really to find out cos of x, to find out the derivative of cos of x and the derivative of sine of x. But we need to develop a way of breaking up breaking this up, a plus b. This here we need to find a way of breaking this up. We need to find out a way of breaking this up as well. Okay, so so in the next video I will try and explain these two. But don't forget, I still owe you an explanation for these three cases here. Okay.